Hi class, today I'd like to share with you how I use chemistry in my everyday life. Every single Saturday, my daughter and I make a big batch of crepes. It's a wonderful way to have a nice big weekend breakfast, and we even save a bunch so that we can heat them up and have a delicious breakfast all week long. Now, there's a lot of chemistry concepts that occur when you're making crepes. The first one is we use a recipe. Recipes give exact quantity relationships between the items that you have to put into the recipe and the number of pieces you get out of a recipe. So in this recipe, you need 1 cup of flour and 2 eggs and a half a teaspoon of salt to make 5 crepes. Now, the world isn't so perfect. Sometimes we want to make a really big batch of crepes. So what if I wanted to make 15 crepes? I can use the recipe to find the relationship that can tell me how many eggs I would need in order to make 15 crepes. So when we look at this recipe and we compare it to a chemical reaction, we know that all of the items put in are called reactants. And what you make or your new substance is called the products. So the balanced chemical equation is so much like a recipe that it gives the relationship between the amounts of reactants to the amounts of products. How many eggs would be required to make 15 crepes? So I can just underline, I'm looking for the number of eggs to make 15 crepes, and I can set up 2 equivalent fractions. So 2 over x equals 5 over 15. So in order to clear the denominator, I'm going to cross. And so I will see that I need to have 6 eggs in order to make 15 crepes. So let's say I had 5 eggs in my refrigerator and I wanted to use them all. How much flour would I need to completely use up the 5 eggs to make crepes? Really special about this relationship is it's not only reactants to products, but it's any substance in the equation. Say I have some eggs that are about to go bad and I want to use them up. If I have 5 eggs in my refrigerator, how many cups of flour would I need to make crepes with all 5 eggs? So I can set up a proportion again. And I'm getting my proportion or my fraction by just underlining and write what I know underneath. So once I have this, I see that 2x equals 5. X equals, so I will need 2.5 cups of flour in order to completely use up all 5 eggs. Chemical reactions, like this one seen here, are just like recipes. The large number in front of each formula, called the coefficient, tells you the quantities of each species that are needed to produce the products. So in this equation of photosynthesis, 6 carbon dioxide and 6 moles of water will produce 1 mole of sugar and 6 moles of oxygen. But what if I wanted to make 3 sugars? Chemical reactions work in exactly the same way. So in order to produce glucose, wheat uses photosynthesis. This is the reaction. And so we have these compounds and we're going to break their covalent bonds and form new covalent bonds as they undergo photosynthesis. From this balanced reaction, you can see that I require 6 moles of water in order to produce 1 mole of glucose. So in this reaction for photosynthesis, the question is, how much water is required to produce exactly 3 moles or units of glucose? So what we're going to do is we're going to set up fractions based on our underlying quantities. So I'm going to take the coefficient here, 6 over x, because I'm looking for that, equals, now there's no written coefficient here, but it's understood to be 1. And then I'm going to clear my fraction. And I'm going to need 18 units or moles of water to make exactly 3 glucose. When I start making crepes, the first thing I need to do is light my stove and warm up the pan. To light my stove, I'm going to use combustion. Combustion is a chemical reaction where bonds are broken and new bonds are formed. The properties of the products are completely different than the properties of the reactants. In combustion, the products are always carbon dioxide and water. When we look here at this combustion of propane, notice how the coefficients, or the large numbers in front of each formula, serve the purpose not only to give us the perfect recipe, but to give us the perfect recipe that conserves matter. That means that the number of each kind of atom is the same on the reactant side to the left of the arrow as it is to the product side to the right of the arrow. Look at these scales that can show you how each species is equal on both sides of the reaction. After my pan is hot, I'm going to melt butter. Melting butter is a physical change, not a chemical change like combustion. Melting is an example of a physical change because no new bonds have been created. I begin with butter and I end with butter. The only thing I am changing is the phase of matter. When we melt, we add heat. When heat is added, it makes this phase change endothermic. Butter has a greater intermolecular force than milk. That's why butter is solid at room temperature, but milk is a liquid. The higher the melting point of a substance, the greater its intermolecular force is. Butter, which has more intermolecular forces, has a definite shape and a definite volume, while milk has a definite volume, but it has no definite shape. It takes the shape of its container. Once I make crepes, the process of cooking crepes is another chemical change. During this chemical change, the crepe batter forms new bonds, which give it entirely new properties. Raw crepe batter is a liquid at room temperature, but cooked crepe batter is a solid at room temperature. When trying to identify a chemical reaction, scientists need to assess whether or not the properties, such as melting point, boiling point, density, and reactivity, have actually changed. But there are several evidences of a chemical change that we can look at that could indicate the likelihood of a chemical change. When cooking crepes, we'll watch the batter change color from a pale white color to a toasty brown color. We'll also have an odor change. When my crepes are done, I like to top them with Nutella. Nutella is a homogeneous mixture. We know Nutella is a mixture because its components of hazelnuts and chocolate are only physically combined. They are not bonded together. They maintain their individual properties, but they are evenly mixed throughout, making it a homogeneous mixture. That's why if you were to eat a jar of Nutella, the first bite and the last bite in the jar would all have the same flavor because homogeneous mixtures are uniformly combined. They also can never be separated by filtration. Well, that's all I can think of as how chemistry comes into my life every Saturday as I make crepes with my daughter. I hope you enjoyed this, and I look forward to seeing your project.